Welcome to the lecture on quadratic functions and their graphs. We're going to start by talking about the basic x squared function. Now hopefully this is a function that you already know the graph of, and you also know some other properties about it like domain and range. So let's quickly review that. The x squared function is a parabola centered at the origin with a vertex at the origin, and the pattern that we use to graph a parabola is starting at the vertex, which is 0, 0. We go over 1, up 1 to get to one key point, and then we do that on the left side as well, over 1, up 1. So we get these two side points, and then to get a couple other side points from here you can go over 1, up 3, and over 1, up 3 on the left side. So you get these 5 points, the vertex, and then 2 side points on each side. So that's this pattern over here that you want to kind of have memorized. It helps you to get a good, nice, clean graph of a quadratic function. So over 1, up 1, over 1, up 3. If we had to go higher, the pattern does continue and go over 1, up 5. It would even continue farther and go over 1, up 7, and so on. So we're going up vertically all these odd numbers. The domain of a quadratic function is all real numbers because no x is restricted. We're allowed to use any x that we want and plug it into this function. The range, on the other hand, if you look at your graph, the graph doesn't go any lower than the value 0, the y value 0. So my range is starting at 0 and it goes up from there. So our range would be 0 to infinity with a bracket around the 0. The vertex of x squared, as we mentioned already, is just the origin, 0, 0. When you hear the phrase minimum value refers to the y value, the smallest y value that the graph goes through, and we know from our range that that smallest y value is 0. So this would just be 0. And then finally, the axis of symmetry. This may be new terminology for you. This is a vertical line that bisects or intersects your graph and cuts it in half. So it's going to be the line that goes straight through that vertex so that you divide that parabola in half. So the equation of this line, because it's a vertical line, is going to be x equals, and since the x coordinate of the vertex here is 0, this is going to be x equals 0. Please make sure that when you're writing an axis of symmetry, you don't just write 0. It needs to be the equation of a line, so it should be x equals. Okay? So what we're going to do next is basically transform this x squared function by shifting it left, right, up, down, flipping it over, stretching it, shrinking it, all those good things. So we're going to start with this next example where we have the function x plus 2 quantity squared minus 3. So this is starting with the basic graph x squared, and we're performing a couple of transformations on it. What transformations are we doing? Well, remember that when you see a plus 2 on the inside of these parentheses, so that 2 is also going to be inside of that square, that's called a horizontal shift, and it's backwards from what you would expect. So plus 2, we think go to the right 2, but actually we're going to go left 2. So our transformations, or sometimes these are just called translations, the first transformation we have here is that we're going to go left 2, and that's called a horizontal shift. And then we also have this minus 3 on the end. Anytime you have a constant on the end outside of your square, that's going to be a vertical shift. And this does do what you would expect. So a minus 3 means we're going to go down 3 vertically. So we have two transformations, left 2 and down 3. Now if you remember that pattern that we talked about earlier, it's really quite easy to get the graph of a quadratic if you know the pattern and you know what shifts are happening. So the first thing you want to do is identify where your new vertex is going to be. Normally, x squared would start at the origin and we'd go over 1, up 1, over 1, up 1, and then over 1, up 3, over 1, up 3. So we'd get that U shape. So what we're doing to this function, this x squared, is we're shifting it left 2 and down 3. So I'm going to move just the vertex, that's the only point I'm going to work with at first here, and move it left 2 and down 3, and that's where the new vertex is going to be. So right away we know the coordinates of this vertex are going to be -2, comma, -3. Notice that that vertex just so happens to come from these numbers that we see up here. The x value is the opposite of the number we see inside the parentheses. So we see a +2 here, we use a -2 in our vertex. And the number on the end, this -3, we use exactly that same number for the y value of our vertex. So that's a good thing to look for. If we have these transformations written out very nicely for us, we just take the opposite of this inside number for the x value and the same number for our y value. And that's going to be our new vertex. Once we know our vertex, then we're going to use our pattern. So remember the pattern. Once you know your vertex, you go over 1, up 1 on both sides, and then we go over 1, up 3 on both sides. So if I do that here, here's my new vertex. Over 1, up 1 on the right, over 1, up 1 on the left. From those two side points, I'm going to go over 1, up 3 on the right, and over 1, up 3 on the left. And that gives me 5 good points to plot so that I get a nice parabola. You could do more if you wanted to, but 5 is a good starting point. So here's my new graph, the one in red. This is that x plus 2 squared minus 3. The domain of this parabola isn't going to change. The domain of every single quadratic is always all reals. There's no restrictions on what x can be. The range will change because I've shifted this graph down. So instead of only going as low as 0, now I go as low as -3, and then I go up from there. So my range is -3, including the -3, so I have a bracket, up to infinity. If you know the range, then you also know the minimum value here. This is a parabola that's pointing up, so it's going to have a minimum right at that vertex, and the y value of that vertex is your minimum value, which in this case was that -3. And then finally the axis of symmetry. Remember that that's going to be the vertical line that cuts our parabola in half. Because it's a vertical line, it's always x equals, and the x value of the vertex was -2, so our axis of symmetry is also x equals -2. Okay, now this particular example did not have any stretches or shrinks, vertical stretches or shrinks. And that's what we're going to talk about next. The only transformations we had in this problem were horizontal shifts, left and right, and vertical shifts, up and down. So if we take a look at this next formula, this is going to be a very generalized formula called the Vertex Form of the equation of a parabola. And what it says is that in its most general form, you can write every quadratic as y equals a number a, parentheses, x minus h quantity squared plus k. And the significance of these numbers a, h, and k is really important. Remember what we said in our last example, how the vertex, -2, -3, came from the number inside the parentheses using the opposite sign and the number on the end outside of that square. Well, that's what this is saying here as well. If I have a -h, then I'm going to use +h for the x coordinate of my vertex. And if I have a +k on the end, I'm going to use +k for my y coordinate. So the numbers that we see inside the parentheses and outside give you the coordinates of your vertex right away. Similarly, that y value, that k, is going to be your minimum or your maximum value. In the case of a being positive, we're going to have a parabola that points upwards. So if you have a positive, this is going to be a parabola that goes up. If a is a number that's negative, this is going to be a parabola that points down. In the case of a being positive, we have a minimum. In the case of a being negative, we have a maximum. So if we have a min, that's going to be when the coefficient out here, this a, is positive, and we're going to have a max when a is negative. Regardless of which case it is, that k value of your vertex, the number on the end here, is going to be that min or that max value. The domain of every parabola is always all real numbers. The range will change. If we have some vertical shifts, that's going to affect our range. So the range is going to be k to infinity if we're pointing up, because if you look at this picture here, the y value of this vertex, h comma k, is at a height of k, and we go up from there. So your range is going to be k to infinity if your a is positive. If your k is negative, if your a is negative, then you have the parabola that's pointing down. So this time your range is going to go no higher than k. So your range is minus infinity up to k. Okay? Then the pattern that we talked about earlier is going to change slightly. Instead of going over 1, up 1, over 1, up 3, because we have this a out front, we're going to have what's called a vertical stretch or a vertical shrink, or sometimes it's called a vertical compression. And what that does is it affects sort of the steepness of your graph. If this number a is bigger than 1, like 2 or 3 or 5, then what's going to happen is our graph will get narrower. So we're going to get a skinnier parabola than what we had before. And this is called a vertical stretch. If you have an a that's between 0 and 1, like a fraction, like a half or a third, then that's going to make the graph get wider, like this, and that's called a vertical compression. How steep and how wide we go is determined by that a. So the pattern, instead of being over 1, up 1, is now going to be over 1, up a, and instead of going over 1, up 3, now we're going to go over 1, up 3 times a. And if a is negative, we do the same thing, but we go down instead of up. So we're going to go over 1, down a, over 1, down 3a, and we do that both on the left and the right side of the vertex. So that's a lot of information to know, but you want to kind of have it memorized. Let's practice and put it all together. So in this next example, we have y equals 3 parentheses x minus 3 squared minus 2. So the first thing that you always want to figure out is your vertex. Your vertex is going to be that key starting point before you can apply your pattern. So our vertex here is going to be the opposite of this number inside of the parentheses. So if I see a minus 3, then the x value is positive 3. The y value is exactly the same number that we see on the end here, so that's going to be that minus 2. In terms of transformations, this minus 3 is going to be a shift right 3 backwards from what we would expect, and then the minus 2 on the end is going to shift us down 2. And then this 3 that's out front, remember up here how we said if that a is bigger than 1, that's called a vertical stretch. So this 3 is going to stretch us vertically by a factor of 3. So that's what that 3 does. If we wanted to graph this new parabola, start with that vertex. So we're going to go over 3, down 2, put a dot, and now we're going to use our pattern. First of all, does this parabola point up or point down? Because our 3 out front was positive, this parabola points up. So when we use our pattern, we're going to want to make sure that we go over 1, up a, over 1, up 3 times a. So we're going to go over 1, up a, and a here was this 3. So we're going to do that on the right and the left. And then we're going to go over 1, up 3 times a, so 3 times 3 would be 9. And that's going to get pretty steep pretty fast, so we may actually go off of our graph doing that. So here's our vertex. We're going to want to start by going over 1, up a. A was 3, so I'm going to go up 1, 2, 3. And I'm going to do that on the left side as well. Over 1, up 3. So there's 2 side points. The next side point would be over 1, up 9, 3 times 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We're going to be way up here somewhere. And on the same side, on the left side, doing the same thing. Over 1, up 9. We're going to be way up here. So we get a graph that's much skinnier than it was before because we've vertically stretched it in. And my V here is a little bit pointy. It should be more rounded, like a U shape. Okay, so there's our new parabola. To review a couple of other things here, the domain, remember, would be all reals. That's not going to change. The range is going to be your lowest point up to infinity. So here our lowest y value is at a height of -2, and I go up to infinity from there. My axis of symmetry is going to be the vertical line that goes through the x value of the vertex, which was at 3. So this is just going to be x equals 3. And do we have a maximum or a minimum here? Because this is a parabola that's pointing up, we have a minimum. So we have a minimum value of whatever this y coordinate is of the vertex. And that was -2. So our minimum value is -2. Okay, so let's try all of that again with another example. So here we have -2 x plus 1 quantity squared plus 4. So for our transformations, this time we have 4 different transformations. We have the plus 1 on the inside. Remember, that's a horizontal shift, either left or right, backwards from what you would think. So a plus 1 is actually going to make us go left 1. The plus 4 on the end is going to make us go up 4. The 2, because that's a number bigger than 1, is going to be a vertical stretch. So we're also going to have a vertical stretch by a factor of 2. And the other transformation which you might overlook is the negative in front of that 2. What a negative does is it's a reflection over the x-axis. So in terms of our pattern, that means that our leading A here is -2, a negative number. So instead of a parabola that's pointing up, like our last example, now we're going to have a parabola that's pointing down. So when we use our pattern, we're going to go over 1, down A, over 1, down 3 times A. So let's figure out where that vertex is first so we know where to start. So the vertex is going to be, for the x value, the opposite sign of what we see in the parentheses. So we have a plus 1, so our vertex is going to start at -1, and the y value is the same number we see on the end, so that's going to be +4. So going to -1, 4, I'm going to put my dot for my vertex, and now we're going to use our pattern. Our pattern is to go over 1, and this time remember A was -2, so we're going to go over 1 on both sides, down A, and then over 1, down 3A. So since our A is -2, we're going to go over 1, down 2 on the left and on the right. Then 3 times that is going to be 6. So now we're going to go over 1, down 6 on the left and on the right. So over 1, down 6. These should be nice and symmetric. And here we get, again, another kind of skinny parabola. The bigger that coefficient is, the skinnier your parabola is going to get. So there's our new graph. The domain of this parabola is all reals. That hasn't changed. The range this time is not going to be start at your lowest value and go up like the last problem. This time our range starts down here at the bottom at -infinity and stops at that y value of the vertex, which in this problem was 4. The highest value we hit was 4. So our range here is -infinity up to 4 with a bracket. The axis of symmetry is going to be the vertical line x equals, and the x value of that vertex is -1. And this time, instead of having a minimum value, because this parabola points down, we now have a maximum value, and the maximum height we went through was the y value of our vertex, so our maximum value is 4. Okay, on these next two, we're just going to practice our graphing. You can find all the rest of that information if you like, but let's just work on our graphing here. So on this next example, we have 1/2 x plus 2 squared minus 3. So let's find our vertex first. The vertex is the opposite sign of what we see in front here. So this plus 2 means we're going to have a vertex at -2, and a minus 3 on the end means our vertex is now at -2, comma -3. So I'm going to go ahead and put a dot there, over 2, down 3. Now this time our a is 1/2. That's a fraction, so this is going to be what's called a vertical compression by a factor of 1/2. The plus 2, remember, is shifting us left 2, and the minus 3 is shifting us down 3. So those are all of our different transformations. How does this vertical compression affect our graph? Well, the first thing you want to notice is that it's positive. It's a positive 1/2. So our parabola needs to be pointing upwards. So we're going to start at our vertex, and we're going to go over 1, up a, and in this case, a is 1/2. So we're going to want to go over 1, up 1/2 on the left and on the right. So if here's my vertex, over 1, up 1/2, over 1, up 1/2. Then if I wanted to get a couple more side points, we would want to go over 1 again, but this time we'd want to go up 3 times a, which is going to be 3 times 1/2, and 3 times 1/2 is 1.5, 3/2. And we're going to do that on the left and on the right. So we're going to go from this little side point over 1, up 1.5. So that should put you right at a height of -1 if you're doing those two side points correctly. So here's my graph. It's a little bit wider than a normal parabola would be because we compressed it out by 1/2, kind of pushing it outwards. So here's our new graph. Okay? Let's try that again over here. On the next one, we have a minus sign, which is that reflection over the x-axis. We have an a, which is a third. That's going to be a vertical compression by 1/3. So again, that's going to make our graph wider. We have a -1 in our parentheses, which is going to be shifting us right 1. And then we have this +2, which shifts us up 2. So our new vertex is only affected by the horizontal and vertical shifts. So we have a -1, so my vertex is at +1, and then we have a +2 on the end, so the y value is +2. So my vertex is going to be at 1, 2. Now the a here includes the negative. So a here was negative. That means we want to be pointing downwards. So in our pattern, we're going to start at our vertex, and we're going to want to go over 1, down a, which in this case was that 1/3. So we're going to have to kind of approximate that a little bit. We're going to go over 1, down about 1/3, over 1, down about 1/3. To get a couple more side points, we'd go over 1, down 3 times a, so 3 times 1/3 is 1. So from this point on the side, we're going to go over 1, down 1, so that's still going to be at, oops, sorry about that, we're still going to be at a little fractional amount. This time we're going to be at a height of 2/3 when we end up. So we're going over 1, down 1. So we get this parabola, again, that's a little bit wider than a standard x-squared graph. Okay? Notice this has a maximum height of 2, and the one we did over here had a minimum value of -3. Okay, so that vertex form is really useful because if you have your parabola written in vertex form, it's very obvious where your vertex is. I can just look inside the parentheses at that h and that k, and I know where my vertex is. And if you know your vertex, then it's really easy to graph by just using your pattern, over 1 up a, over 1 up 3a. So we really like the vertex form equation of a parabola because it makes all that important information obvious, and it makes graphing very obvious. So what happens if you have an equation of a parabola that's not in that vertex form? For example, right here, x squared plus 8x plus 7. We don't have a quantity squared. We don't know what our h is. We don't know what our k is. So this isn't going to be as nice to work with in terms of graphing as the other examples that we did. So what we're going to want to do is put this into vertex form. And the way that you do that is by completing the square. So on this example, what we're going to do to complete the square is we're going to take our function, which was x squared plus 8x plus 7, and the first step that I'm going to make when I complete the square, normally when we solved equations to complete the square, we took our constant and we put it on the other side of the equation. I am not going to really do that here because I'm just working with this right-hand side. I'm not really working with a whole equation. So what I'm going to do instead is just take that plus 7 and push it off to the side. It's still there, but I'm leaving room so that I can add and subtract in those sort of missing constants that I need when I complete the square. Now remember the process of completing the square. You need that leading coefficient to be a 1. This one is, we get a little bit lucky. If it wasn't a 1, then you would have to factor out that coefficient from all 3 of these terms, or at least these first 2 terms. Once I have that leading coefficient to be a 1, then we're ready to do our process of completing the square, which says you always take 1/2 of the middle coefficient. So here my middle coefficient is positive 8. Half of 8 is 4. That 4 is what's going to go in our quantity squared. So x plus 4, when I square this out to double check it, I should be getting back what I started with. I'll get the x squared, and I'll get 2 middle terms that add up to an 8x, but what I'm missing is the 4 squared if I were to FOIL this out. And I don't have that 16 up here that I would get when I square 4. So what we're going to do is take that 4, square it, that's what we're missing, so I'm going to add it and at the same time subtract it, so that I'm really just adding a big fancy 0 right here. However, with a little creative grouping, these 3 terms turn into my completed the square form, my perfect square right here. But on the end, what we're going to have are these 2 constants. And if I combine them, negative 16 plus 7, that's going to give me a minus 9. So look at what we've done. We've taken x squared plus 8x plus 7, and we've rewritten it as x plus 4 quantity squared minus 9. Notice that that is our vertex form. It should be very obvious from here what your vertex is. The vertex is going to be the opposite of this number, so negative 4, comma, for the y value, the same number we have on the end, so minus 9. So if we plot that, negative 4, negative 9, which is just down here below my lines. I don't have a quite big enough graph. So there's my vertex. And now we want to graph some side points. To graph the side points, look at what your a is. The a that we have in the original function is this coefficient of that x squared, and that's the same coefficient that we should have down below out front here. I don't have anything there, so it's implied to be a 1. So in this problem, a is 1, positive 1, so we should be pointing up. And in terms of my pattern, I'm just going to need to go over 1, up A, and since A is 1, I'm going to go over 1, up 1. And then to go some more, I would go over 1, up 3 times A, so 3 times 1 is 3, and I'm going to do that on the left and on the right. So from my vertex, we're going to go over 1, up 1 on the right, over 1, up 1 on the left, over 1, up 3 on the right, over 1, up 3 on the left. And here is my graph. There's no stretching or shrinking here, so this should look like a normal parabola that's just been shifted left 4 and down 9. And those were the only transformations that this graph had. Now, completing the square is probably not most people's favorite thing to do. So lucky for us, we actually have an alternative. Instead of completing the square to get your vertex equation, what we can do is take any quadratic function, ax squared plus bx plus c, and using the completing the square process on this general form, we end up finding that the vertex is always going to be determined by using this formula. So this is called the Vertex Formula. It turns out that the x value of your vertex is this minus b over 2a. So using the a, the b, and the c from the original quadratic, those coefficients, the x value of the vertex will just be minus this b coefficient divided by 2 times the a coefficient. Once you know x, you can plug that back into this function to find out what y is. And sometimes the way we write that is you take that minus b over 2a, which was x, and you input that into your function. And whatever you get when you plug it in, that's going to be your answer. Okay, so for example, here's 2x squared plus 4x plus 5. You could complete the square on this, but that gets a little bit tricky sometimes. So instead, we're going to use our vertex formula, which says that x equals minus b over 2a. So here my b is this 4, and my a is the 2. If we simplify that, we get negative 4 over 4, which is negative 1. So right away, I know that the x-coordinate of my vertex is negative 1. To get the y value, we have to substitute in negative 1 into this function. So we're just going to plug negative 1 in for all these x's. So that's going to be 2 times negative 1 squared plus 4 times negative 1 plus 5. And that's going to be 2, because negative 1 squared stays 1, minus 4 plus 5, and that simplifies to 3. So my y-coordinate of my vertex is 3. So right away, I know my vertex is at negative 1, 3. To get the graph of this, you can transform your general form here, your standard form of your quadratic, and you can think of it in vertex form. So the vertex form that would be equivalent is going to be that a parentheses x minus h squared plus k. That was our vertex form. So in this equation, what's a? It's the same a that we had in the original problem, that coefficient of x squared. So a is 2. Then we'd want parentheses x minus h. Well, what was h? Remember, h is that x-coordinate of that vertex using the opposite sign. So if my x-coordinate is supposed to be minus 1, then I need to have a plus 1 in parentheses squared so that the opposite number will match up. The k is the k of the vertex, which was our 3, so I'm going to use a plus 3 on the end. So that's how you take your standard form and you rewrite it in vertex form. So these are equivalent if you were to expand all this out. So in terms of graphing, we have our vertex at negative 1, 3, and now notice here that a is 2, positive, so we're going to go up, and our pattern is to go over 1, up a, so we're going to go over 1, up 2. If we wanted some additional side points, we'd go over 1 up 3 times a. 3 times 2 is 6. If I did that on my graph here, that's going to put me way off my graph. So I'm not going to show any more additional points because my grid isn't quite big enough. But you could do that if you had a larger grid. 3 points is enough to get an idea of what this parabola looks like. So there's my graph. Okay? The domain, let's review that again, is all real numbers. The range here is going to be whatever your lowest value is, and this height is 3, and from there we go on up. So our range is 3 to infinity. Does this parabola have a maximum or a minimum? Because it's pointing up, it's a min, and that minimum value is that y value of that vertex, which we said was 3. Now another couple things that sometimes you want to investigate when you're graphing is finding intercepts. Looking at or graphing a graph really completely on a grid, it's useful to know where does it hit the x-axis and where does it hit the y-axis, and that gives you a nice complete picture. So sometimes questions are going to ask you to find x-intercepts and y-intercepts. So I wanted to review that with you. To find x-intercepts, you let y be 0 and you solve for x. To find y-intercepts, you let x be 0 and you solve for y. Now y-intercepts are always easier to find for these quadratic functions because if I have the function 2x squared plus 4x plus 5, all I have to do is substitute in 0 for these x's. So that would be 2 times 0 squared plus 4 times 0 plus 5, and that's going to give me the y value that I'm looking for. Well, since these are zeros, this goes away, and we always end up with just that constant on the end. So your y-intercept will be really easy to see. It's always going to be the constant term. So on my graph, that should correspond to where my parabola is hitting the y-axis. And if we look up here, here's my y-intercept, and indeed it is at a height of 5. So that does match up with that y-intercept that we found. Okay, so let's take a look at x-intercepts now. These are harder to find because this time we're going to let the y be 0. So if you look at your original function, where's y up here? Well, you want to remember that y is the same as f of x. So we're going to be putting the 0 on this side of the equation and trying to solve for x. So let's go ahead and do that. We're going to put 0 on the left side and set it equal to our function, 2x squared plus 4x plus 5. Now, if you get lucky, this will be a quadratic that factors. This one will not. No combination of 2's and 5's is going to give me a 4 for that middle term. So if it doesn't factor, your alternatives would be to either complete the square or quadratic formula. So let's review that quadratic formula. The solutions by the quadratic formula are going to be for x, and what the quadratic formula says is x equals minus b, which in this case is the opposite of this positive 4, so negative 4, plus or minus the square root of b squared, so 4 squared, minus 4 times the a, which is 2, times the c, which is 5, all over 2 times a, 2 times 2. Now we want to simplify. So in the denominator, 2 times 2 is 4, and under the radical, 4 squared is 16, 4 times 2 is 8, 8 times 5 is 40, so this is 16 minus 40, which simplifies under the radical to a negative 24. Now I can stop here. That's not a reduced radical, and it's not going to be a simplified fraction. I could probably clean this up some more. But in terms of my graphing, I can stop, because as soon as you get a negative under that radical, we know that this is not a real number. It's a complex number. It would have i's in it. We cannot graph i's on our graph over here. We can only graph real numbers. So what does that imply? If you're getting a negative under the radical for your x-intercepts, then that means there are no x-intercepts that are real numbers. So this means there are no x-intercepts at all that I can graph. So let's verify that. When you look at your graph up here, there were no x-intercepts because this graph is completely above the x-axis and it points up. So it never crosses that x-axis to begin with. So I should have predicted that from the beginning that I wasn't going to get any. Okay? So finding x-intercepts and finding y-intercepts. You're letting 0 be y and 0 be x in solving. And these are just additional points that sometimes you want to find to make your graph become a little bit more complete. Okay? Alright, we're going to practice all that one more time on one full example. Typically when I ask questions about this stuff, this is exactly all the information that I want to find. I'll give you a function and I'll ask for the vertex, the domain, the range, the max or the minimum value, the intercepts, and a graph. Sometimes I'll even ask for what transformations have been applied. So if we are given this function right here, remember that this is not in vertex form. It's in that standard form, which isn't as useful for graphing. It's not obvious what that vertex is. So what we can use is that vertex formula. This is a special formula that you want to have memorized. And what the vertex formula says is that the x value of your vertex is always minus b over 2a. And we're just going to plug in what our b and our a are for this particular function. So b is negative 2. Make sure you take the sign with it. So we want minus negative 2 all over 2 times a. A is the coefficient of x squared, which includes that negative. So here a is negative 1. So on top we get 2, on the bottom we get negative 2, and this reduces to negative 1. So my vertex automatically has x coordinate negative 1. For the y coordinate, you get it by plugging negative 1 in for these x's. So we're going to figure out what f of negative 1 is. So that's going to be minus negative 1 quantity squared minus 2 negative 1 plus 3. This negative 1 goes away to a positive 1, but the minus out front stays there. So this simplifies to negative 1. Negative 2 times negative 1 becomes positive 2. So we get 5 minus 1, which is 4. So our y value of our vertex is 4. So now we have our vertex, negative 1 comma 4. So we can plot that right away. Now before we plot the rest of this, let's go ahead and find some of these other things. When we're making a graph, finding these intercepts is sometimes helpful to give us that complete graph. So let's go ahead and find our intercepts next so that we can plot a couple of more good points. Remember that your x-intercepts are going to be where y is 0. And y up here is this f of x. So we're going to put 0 right up here on the left side and set it equal to our function. So we're trying to solve 0 equals negative x squared minus 2x plus 3. This one has a negative leading term. It has a good potential of factoring because there are ways to take factors of 3 and get a 2 out of it. But if you don't like that leading term being negative, all you need to do is just move all your terms to the left side, and that switches all your signs around. In other words, we're just multiplying through by a negative 1. So that gives you a positive leading term, so it's a little more obvious how to factor. So I need x times x to get x squared, 3 times 1 to get 3, and in order to get a positive 2 in the middle, I need to make the 3 plus and the 1 minus. And so my two solutions are going to be negative 3 from this factor and positive 1 from this factor. So in this example, we do have two x-intercepts, negative 3 and 1. So to plot those, you go to your x-axis and you're going to put a dot at -3 and +1. So I know that my parabola needs to cross through those points. Let's find our y-intercept. The y-intercept is going to be where x is 0, and that should be easy to find because you're just going to substitute in 0 here and here. So that's going to be minus 0 squared minus 2 times 0 plus 3. And these zeros are going to go away, so we're just going to end up with a y value of 3. So my y-intercept is at 3 on the y-axis, so I have a dot right there as well. So we're just kind of adding some extra points on our graph. Now let's finish off our graph using our pattern. What is a for this particular function? A was this leading coefficient, so a is -1. Because it's negative, this is a parabola that needs to point down. And our pattern is going to be start at the vertex, go over 1, down a. So here a, we're going to go down 1. And then from there we're going to go over 1, down 3 times a. So that's going to be 3 times 1 or 3. So this time we're using that same pattern but going downwards. So here's my vertex. Over 1, down 1 gets me to that y-intercept that we already had. That's on the right side. Now let's go over 1, down 1 on the left side, so we get that symmetric point. Then from those 2 points, we'd want to go over 1, down 3, and over 1, down 3, which just so happens to be our 2 x-intercepts. So we now have all of our 5 points, so we can get a nice graph of our parabola. Okay? Domain. Domain of this parabola, all real numbers. It's always going to be the case. What would be the range here? Because this parabola is pointing down, your range starts down here at the bottom and goes no higher than that vertex. And the vertex was at a height of 4. So my range is -infinity up to 4 with a bracket around the 4. Do we have a maximum or a minimum in this problem? We have a max because this is a parabola that's pointing down, and that maximum height is again that 4. And just as one last comment on this example, remember that you can take this standard form and transform it into vertex form by using the vertex that we know it needs to go through. Remember, vertex form is supposed to be a parentheses x minus h squared plus k. So if we use that here, what's the a that needs to go out front? It should always be the same a that you used earlier, that leading coefficient of x squared. So this a was a -1, or just a minus sign. Then we'd want x, and then inside of these parentheses, that h, remember our vertex went through -1 for the x value, so we want the opposite sign of that inside of our parentheses. So we need a +1 quantity squared. Then the number on the end, that k, should be your y value of your vertex, so this is going to be +4. So there's your vertex form, and it also, in that vertex form, tells you your transformations that have been applied. The negative is a reflection over the x-axis. The +1 shifts you left 1, and the +4 shifts you up 4. So all of these things that I've just talked about in this problem are all the things you need to be able to do and find for any general quadratic function. So be able to find the vertex, that's probably the most important thing. Be able to get a graph. Be able to find intercepts. Be able to determine the max and the min value, the domain, the range, what kind of transformations have occurred. There's only one thing that I left off the list here, and that would be axis of symmetry. And here, remember that axis of symmetry is the vertical line that cuts right through that vertex. It's going to have an x equals -1, since that was the negative, or that was the x value of our vertex. So that would be the only other thing on this list that I didn't talk about yet. So everything on this problem you want to be able to do. Okay, one more example. We're not going to go into quite as much detail as the last problem. Here's my f of x equals 1/2 x squared plus 2x minus 1. I want to graph this, so to graph it you must know the vertex first. So let's find our vertex using the vertex formula. So the vertex formula says that the x coordinate of your vertex is always minus b over 2a. So in this problem, b is the coefficient of x, so that's 2, and a is the coefficient of x squared, that's 1/2. So on top we get negative 2. On the bottom, 2 times 1/2 is 1, so this whole thing reduces to negative 2. So that's the x coordinate of your vertex. To get the y coordinate, you just plug negative 2 in for these x's. So 1/2 negative 2 squared plus 2 times negative 2 minus 1. You can use your calculator for this. Negative 2 squared turns into 4. Half of 4 is 2. 2 times negative 2 is minus 4. So I get 2 minus a 5, so this is going to be negative 3. Alright, so there's my vertex, negative 2, negative 3. Now to get my graph, I also need to keep in mind what my a is. Here a was that leading coefficient, 1/2. Because it's positive, we want to point up. And for our pattern, we're going to go over 1, up a. So in this case, over 1, up 1/2. And then over 1, up 3 times a. 3 times 1/2 would be 3/2, or 1.5. So let's do that on our graph. Here's my vertex. I need to go over 1, up a. So over 1, up 1/2 on the right and on the left. Then from that side point, I'm going to go over 1, up 3 times a. So 3/2, which is 1.5. So up 1 and another 1/2. So this should end you up at a height of negative 1. So here are my points, and here is my graph. It's a little bit wider than a normal parabola because, remember, a was 1/2, and that a is the same a that you get in your vertex formula. So let's figure out what our vertex form is. That's going to be that y equals a parentheses x minus h squared plus k. So for this problem, a we said was 1/2, so that's going to stay 1/2 in our vertex form. We want x plus 2 because our vertex was at minus 2 and we need opposite signs. So we want a plus 2 in the parentheses, and we have a minus 3 for our k, so a minus 3 on the end. Once we have this in our vertex form, then it's easy to identify your transformations. The 1/2 is called, remember, a vertical compression by a factor of 1/2. It's a compression because we're pushing our parabola out and making it get wider. The plus 2 in these parentheses is a shift left 2, and the minus 3 on the end is a shift down 3. So that would be the list of all of our transformations. Okay, the last thing we're going to talk about on this last page of notes is a couple of application problems, a couple of word problems, and how you're going to need to utilize what we've talked about with quadratics to help you answer some questions. So in this first example, we have a projectile is fired straight upward from the ground with an initial speed of 96 feet per second. Then its height h in feet after t seconds is given by this equation, negative 16 t squared plus 96t. Find the maximum height of the projectile. So first let's visualize what's going on. Here's the ground, and we're shooting off our little rocket from the ground. It's going to go up for a while, but because of gravity, gravity is eventually going to pull it back down to the ground. So that's what's going on. Notice that this height function represents the height of this rocket at any moment in time. And notice that this height function is a quadratic function. That's important because if it wasn't quadratic, we wouldn't be able to do what we're going to do to solve this. So we know that this is a parabola. Now, if you know that you are working with a quadratic function, therefore a parabola, where does a maximum of a parabola have to occur? The maximum here has to occur at the vertex. So if we can find the vertex, then we will know exactly the maximum height. Okay? So the key to this problem, we're not going to do a lot of work. All we have to locate is the vertex, and we will know what our height has to be. So we're going to find the vertex. And the way to do that, because this is not in that vertex form, we need to use the vertex formula. And remember, the vertex formula says that x equals minus b over 2a. So in this problem, that means x is going to be minus b. What's b up here? Well, your a is your leading coefficient, so that's this negative 16. The b is the coefficient of your t term here. So b is 96, and a, we said, was negative 16. So on the top, we get negative 96. On the bottom, we get negative 32. Our two negatives cancel out, and 96 divided by 32 is 3. So that's the x value of your vertex. To find the y value of your vertex, you plug in 3, and in this case, we're not really dealing with x's and y's, we're actually dealing with t's and h's, so we're going to plug in 3 for t. So h of 3 is going to be negative 16, 3 squared, plus 96 times 3, and if we punch that into our calculator, we're going to get negative 16 times 3 squared plus 96 times 3, and we get 144. So the key to this problem is finding the vertex. If you're going to have a maximum, it has to occur at the vertex because this is a quadratic that's pointing down. And if you have a quadratic that's pointing down, you always have a maximum at the vertex. To finish off the answer, what is our final answer? Is it 3 or is it 144? So you have to identify what these two values are. One's your x value, one's your y value. So we want just the maximum height. So we want to know which one of these is our height. Well, remember that x was that 3, and we used 3 to plug in for t. So this 3 is actually a time. So this is 3 seconds. So after 3 seconds, this rocket is right here at that peak. So when I plug 3 seconds in, what am I solving for? I'm solving for h. H is a height, and it was height measured in feet. So this 144 is your feet, and that's going to be your height. So what is our final answer? Well, if they are asking for the maximum height, then the only answer you need to give is that 144 feet. So the maximum height was 144 feet. So in these application problems, these word problems where you're trying to find a maximum or a minimum, all you have to do is find the vertex using the vertex formula, find your x and find your y. One of your answers will be the x value, one of your answers will be the y. You just need to identify which one are they really asking for. Did they want to know the x or did they want to know y? And in this particular problem, they wanted to know the height y. Okay, let's try one last example. The Utah Ski Club sells calendars to raise money. The profit P in cents from selling X calendars is given by the equation P of X equals 360X minus X squared. Right away, I want you to notice that this is a quadratic equation, quadratic function, and which way does this parabola point if we were to graph it? This leading coefficient, even though these terms are not in descending order, the x squared term has a coefficient of a minus 1. So here your a is -1. So this is a quadratic because a is negative that has to point down. So if you're pointing down, what do you know? You know that you have a max at the vertex. So question A, how many calendars must be sold to maximize profit? We want to maximize profit. That means we want to find out when that maximum occurs. So if we're going to have a maximum, it's got to occur at the vertex. So all we have to do is find the vertex. And we're going to use that vertex formula, x equals minus b over 2a. So here the b is what? Remember, these are not quite in descending order. It's kind of backwards. If you want to rearrange terms and put the x squared first and then the 360x, your b is that coefficient in front of x. So b is 360. So we want minus 360 all over 2 times a. A here is -1. So we get negative 360 over -2, and this reduces to 180. So x is 180. Let's go ahead and find the y value. To get the y value, we're going to plug in 180 for x into our function. So we're really finding p of 180. So 360 times 180 minus 180 squared. So on my calculator, we want 360 times 180 minus 180 squared. And we get 32,400. Now, you have your vertex. We found our vertex. It's 180 for x and 32,400 for y. When you're answering these questions, the question A wanted to know how many calendars must be sold to maximize profit, and part B is what is the maximum profit. So one of these questions is asking for the x value of the vertex, and one of these questions is asking for the y value. We just need to figure out which one is which. So in the first problem, we have this vertex. Let's write out what our units are so that we can clearly identify what represents what. So this 180 was our x's. What did x represent in this problem? X was the number of calendars. So this is 180 calendars. What did the y represent here? Y was actually your profit, P, in cents. So this is actually 32,400 cents of profit. You probably wouldn't talk about 32,400 cents. You'd probably change that to dollars. So what is 32,400 cents the same as? Just divide by 100 and you lose those 2 zeros on the end. This is the same as $324 in profit. So this is the same as $324 profit. So now getting back to our question A, how many calendars must be sold to maximize profit? Is that the x value or is that the y value? Well, calendars is x, so we want 180 calendars for our answer for part A. Part B says, what is the maximum profit? Which one of these two values here is the profit? That's going to be the y value. So down here, we're going to have $324 in profit. So usually in these word problems with quadratics, You're trying to find a maximum or a minimum, which will always occur at the vertex if these are quadratic. So you always want to find the vertex first, get your x and get your y, and usually they're going to want both, but you need to identify which one is which. So put your labels on it and figure out, do they want x or do they want y? Okay? Alright, that concludes our lecture on quadratic functions and their graphs. Good luck.